So this is repeat of a part of the absorption imaging from the first part of the lecture. It was omitted for technical reasons. And so what you see here now is you have a detector that gives you a response based on different material properties. So alpha is the attenuation coefficient, has to do with the cross sections, density, etc. And now let's create just a numerical example. We have 3 different materials, and this we now simulate by 3 different normal distributions with different averages and different standard deviations, and create a table where we have some response, and we have material labels 1, 2, and 3, and we have the detector value for the corresponding. And the detector value is what you would see through a transmission. If you look at the histograms of that, or at first just sorting up everything, you can see that the intensities are very much around material 1 is the blue curve, part of the curve. You have material 2, which is the orange, and then we have material 3, which is the green. If you look at what the detector sees, then it's something like this, where you have a very large response for the blue part, material 1, and then less response for material 2, and even less for material 3. In the reality, the distribution we have is completely different, but that is due to the exponential function in the negative exponential function in the transfer function of the imaging method. And now let's look at the mammography example, where we again have the attenuation law. We have some distribution of materials, and we have different thicknesses. And this goes in the end as a line integral through the material. And from there, we have 2 attenuation coefficients. We have air, which is 0, so there is no attenuation at all. And we have breast tissue, which has 0, 0, 1. And in the real case, then also, and now as we have a more or less discrete object, we have the integral turns actually into a sum instead. So let's do this model. And here we have a simplified surface. I think I could rotate it. Yep. And this would be our phantom that we are playing with. And now we see that we have attenuation coefficients, 0.01, pixel size equal to 1. And from this phantom now, we are actually going to measure what would the detector see. And the volume would be the alpha times the mask. So that's the thickness of this breast phantom. And then we apply Beer-Lambert's law. So that would be the sum of the pixels in the direction we are looking, and times the pixel size. And then we compute the exponential of that. There is, oops, not meant to. And so that would then look something like this. That would be the radiograph we see. We have a distribution of transmission values, and this would be the transmission image that we see. And from that, we are going to do something and see what happens. We can, for example, compute the thickness of this breast just by taking the logarithm of the signal we get from the detector, and then we get the thickness. Sounds easy. Oh, okay. I have a lot of zeros, so that it didn't like. And then we get something like this. We can see that the thickness of this breast on different positions. First here is just the plain air, and then we can see the thickness increasing like this. So far, so good. Now, if there is something in it, we can also visualize it looking in 3D. That's also a possibility. Using this mplot 3D toolkit. But now if there is an anomaly, say a tumor, then the attenuation coefficient is not the same anymore. So let's look at that example. Let's introduce something that changes. In this case, it's just a box, which is added onto the image. And if we look at this in visualization, we can see that the transmission image all of a sudden has changed here to a mistake. And then you can see that the detector signal is also has an outlier. And that outlier is actually what we want to detect. And now let's reconstruct and see what the thickness is like. And that is, again, not much what it likes. And then we can see that, oops, there is something really ugly. The breast can't be all of a sudden much thicker. So that is also an indication, and that is the information that we later would like to measure. And this is one way of working with the attenuation coefficients in neutron imaging. We are actually now develop methods that we can quantify the water content in a sample within 5% compared to the balance. So it's quite precise, and we can do it in 3 dimensions. Yes. Well, that's the question. So on one side, you know that you can see that there is a shadow region, and that shadow region doesn't belong to that anatomy. So that is the way they do it in the medical imaging. But if you want to quantify what it is, then you need to know the attenuation coefficient, yes. But that's also tabulated values. You have tables that's muscle tissue have that attenuation coefficient, fat tissue has that, etc., etc. Bones have something pretty high. So that is already standardized. That's the same for all humans. Maybe plus minus a little bit how much the people have water the people have been drinking, etc. But these values, they are constants. So they are known pretty much. It's worse if you go into material science, then you don't always know the attenuation coefficient. Then you need to measure it beforehand to know what it's actually what you see. Making the thing even more problematic is that the attenuation coefficient is mostly also energy dependent. So depending on which energy spectrum you're working with, you can get different contrasts. Going into material science, you can even have diffraction effects that you can have abrupt changes in the attenuation coefficients because of diffraction. That's used as a way to do measurements, but you have to be aware that things can happen. So here's a 3D model of this phantom with an anomaly. And it doesn't look so nice, pretty edgy. Then there were some, about this cross. That was also a thing that wasn't completely covered. So here we have this cross and we want to apply thresholds on it. And the histogram looks like this. It's right now, it looks pretty nice. I think if we set the threshold around 5, we should get pretty good result. And let's see, oops, what happens. Okay, in this case, We put it at 0.4, apply it, and we get some thresholded image. And the result looks like this, where you have, actually, the cross is pretty well covered. There are 2 misclassified pixels, so that it's kind of acceptable. If you now would try different thresholds, so here is a whole line of different thresholds to try. Then we can see that the results depend. So if you have a very low threshold, you have many misclassified pixels. If the threshold is increasing, you can see that its number of misclassified pixels is decreasing all the time. And actually at 0.58, there is no misclassification. And then if we go even higher, then you see that you lose again, actually the cross itself. But all pixels that are inside, they are truly the cross. So that was what I missed due to my forwarder who didn't see sub slides. So sorry for that.